Okay, now, no one can breathe while we're doing this so that it continues to charge. Technology at its finest. Doesn't matter where you are in the world. It all stinks. Okay, let's get something on the board here. I want you guys to do other work too today. So, I want to talk about stoichiometry, S-T-O-I-C-H-I-O-M-E-T-R-Y, stoichiometry. Stoichiometry essentially says that there are inherent constant ratios that can be used in proportional relationships to predict products and outcomes based on the mole ratio of the substances in a chemical reaction. Is that well said? That was pretty good, don't you think? Let's take a simple one, okay? First thing you do is you want to write the balanced formula equation. Now I will do a lot of work on teaching you how to write stoichiometric equations from scratch. We'll look at different types of reactions, such as synthesis, decomposition, single displacement, and single, did I say single displacement? Yeah. Single displacement and double displacement, or double replacement and single replacement. They're called replacement and displacement. Replacement and displacement, single and double, either way. Some books call it single displacement, some call it single replacement. Okay, now, enough said about that. So we know that from our talks of the mole, we know this sentence, okay? The mass in grams of 1 mole of particles. And what kind of particles can they be? They can be ions, formula units. What else can they be? Molecules, or what else?
AMUs.
Yeah, no. Atoms. Save that response for when I point to you in a minute, okay? All right? Okay. The mass in grams of 1 mole of particles, these are the particles, is equivalent to the mass of 1 particle in AMUs. Very good. What's AMUs stand for? AMUs, what does that stand for?
Atomic mass unit.
Atomic mass unit. Now, just to make things easier, some of my brethren around the planet may disagree with this. I don't really care. Calculations are not as important as concepts. Please use mass numbers instead of atomic weights. Use mass numbers. What's a mass number? What does that really tell you? The mass number is simply the atomic mass rounded to 1's place, more or less. It's the dominant isotope, usually. It is the number of nucleons in the nucleus. It's the number of protons and neutrons, correct? In the nucleus of the dominant isotope, usually. Okay? So the calculation, make it easy on yourself. You get the right ballpark. And then if you're asked to use atomic weights, you certainly know how to use that. Just decimals are a drag. Okay? All right, understood? So use mass numbers when you're getting the atomic weight of a particle, molecular weight, whatever the case may be. Okay, so so we know that this could be 2, 1, 2 in terms of the ratio, right? Remember we said the ratios of the substances within the chemical reaction. Yes, a substance is a pure material, so pure hydrogen, pure oxygen, pure water. Yes, okay. And that's going to be, or 2 million, 1 million, 2 million, or 2 dozen, 1 dozen, 2 dozen, or 2 trillion, 1 trillion, 2 trillion, or 2 moles, 1 mole, 2 moles, right? Right? Yes? So the mass in grams of 2 moles of hydrogen, written like this, H2, would be what? The mass in grams of 2 H2s would be what? Silence. I mean, I'll forgive the fact that we did this on Wednesday. What's the mass in grams? Let's see. The mass of one particle in AMU. So H2, let's see. Hydrogen is 1, so 2H. So H2 would be 2, right? Would that be right? And then 2 H2s, let's see. 2 2s, let's see here. That would be, I don't know, just, I'm guessing, 4. Am I right? It's a guess. All right. Not as dumb as I look. Okay, so that'd be 4 grams. O2, let's see, oxygen is 16. 2 16s, I don't know, that's too hard for me. That's like advanced math. What's 2 16s? What does that mean? What is it? 32. Excellent. 32. I'm trusting you that that's correct because I don't have a calculator here. So 2 times 16 is 32. You're sure? I'm just trusting you. Okay. Is that right? Can you do that in your head? Can you do mentally math like that?
Yeah.
2 times 16 is 32. Are you right?
Yes.
Excellent. Now, here, this is really hard now. 2H2O, that's like advanced differential calculus. What is that? 36. Okay? 36. Excellent. Now, can I erase this here? Can I erase this? These erasers are just awful. Okay, so let's say instead of 4, do you understand that these numbers are proportional to one another? Do you understand that? So let's say I did 1. 1, what?
Your battery's low again.
My battery's low again?
It's not charging.
It's not charging? Okay. My battery's low again. Okay. Really, really good charge you gave me there, Ava. You know, very good. Excellent. It's a Greek thing, I know. Give rotten chargers, you know. Okay, very good. Okay. Sounds like, is that like an ethnic joke, you know? How do you know Greek? They give you bad chargers for iPods. Is that like really good? Thank you, Ava. Okay, so, what else? We have, so if I have 1 instead of 4, how much would that be? What would I need there?
8.
Yeah, so because it's 1/4 of that. So in other words, can we do it this way? I'm comparing, this is what you do. Are you ready? You write down the constant ratio. I'm comparing what? Kinga, what am I comparing? I'm comparing hydrogen with oxygen, correct? Okay, so it's going to be 2 H2 compared to O2. Isn't that the constant ratio? Yes? Now, what's the number that makes the constant ratio constant? What are the numbers? Well, it's going to be 4 and 32, right? Grams, right? Correct? Isn't that correct? This is all you do. The most complicated this becomes is exactly what I'm doing. That's it. Okay? So that's going to be, let's see, I can do this. 1 over what?
8.
No. How do you get 8? Oh, you did that mental math? Wow. Woo, woo, woo. 32 times 1 divided by 4 is what?
8.
Equals 8 grams. Right? So it's 8 grams. Okay, so it's 1/4. So it's proportional, correct? 4 is to 32 as 1 is to 8. What would water be?
9 grams.
9 grams, very good. 1/4 of 36 is 9 grams. And you could continue to do this. For instance, if I said to you instead, I said to you, okay, I said to you 8, I said to you 64, what would this be?
72.
72. So everything is related, correct? But if I said to you 1.8 grams, that's a little bit more difficult to do in your head, isn't it? Yes? So let's do both. Let's do oxygen first. So it's going to be 2H2 over O2 equals 4 over 32 equals 1.8 over what? Over X, and X equals 32 times 1.8 divided by 4. Do it out. Let's go. Come on, guys. You can do it. 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 What do you got?
14.4.
What is it?
14.4.
14.4. Where? This one here? Okay, 14.4. Now, can you do water really quickly? Does anybody can do water really quickly? This is 14.4. Can I erase this right here? No, you know what? I'm going to leave that in.
16.4.
I'm going to get rid of this. Okay, this is 14.4, right?
Yeah.
So what would this be?
16.2.
16.2. You can either do constant ratios again or simply conservation of mass and simply add the two, right? Easy? Yes? All right, let's do a more complicated one. Okay, hopefully I have enough juice here. Otherwise, we'll just blame Ava. Okay? Okay. Okay, now. So let's do a hard one. Let's say lead 2 nitrate plus sodium iodide right? Aqueous, AQ means aqueous, means a water solution, right? They're ions, right? Yields lead iodide, which is, S means solid, arrow down means a precipitate. It's coming out of solution. And plus sodium nitrate. 2 here, 2 here. You see that, what I did? I balanced it. Yes? We'll work on that. We'll work on that. Okay, good. Now, 1 mole, 2 moles, 1 mole, 2 moles. Correct? Want you to write now, and then we'll come back. I want you to write out the stoichiometric masses. 1 mole of this, 2 moles of this, 1 mole of this, 2 moles of this. Right now. Go. Okay? And I'll come back and I'll put them on when you're all finished. Okay?